Hello all, my name is Cassidy Jacobs and I will be going over Chapter 2 for Introductory Business Statistics today. So let's go ahead and get our PowerPoint pulled up and we will get started. Okay, so Chapter 2 is over descriptive statistics. So descriptive statistics is how we communicate data and statistical information through graphs and charts, tables, and other means. One of the types of tables we use is called a stem and leaf graph or a stem plot. And we like this type because it's really good for small data sets, and it also is wonderful so you can see all the individual data values. So if you were given this stem and leaf plot, you would be able to know exactly what every data piece was. And stem and leaf is one of the few that allow us to have that. Outliers are an observation that does not fit the rest of the data. And so we will see and discuss outliers a little further on in our presentation. So let's take a look at this first example here, example 2.1. So for Susan Dean's spring pre-calculus class, scores for the first week exams were as follows: smallest to largest. Construct a stem plot for the data. So we're going to have two columns. We're going to have our stem, and then we're going to have our leaves. And so it is simply putting in the stems, we're going to put the tens place for this. And in the leaves, we're going to put the ones place. So we're going to start with 33, 42, 49, 49, 53, 55, 55, 61, 63, 67, 68, 68, 69, 69, 72, 73, 74, 78, 80, 83, 88, 88, 88, 88, 90, 92, 94, 94, 94, 94, 96. And I don't have quite enough room, so I'm just going to scroll down a little bit and write it right here. So 10 and 0 for 100. And a lot of times we need a key, and this is just so that everybody understands what the stem and the leaves represent when they take a look at your graph. So our key would look like this, and we would say that this represents 33. So let's do another example, example 2.2. The data are the distance in kilometer from a home to a local supermarket. Create a stem and leaf plot using the data. Do the data seem to have concentrations of values? So let's take a look here. We're going to have a stem and leaf here. But this time our stem is going to represent, we can go ahead and do our key. Our stem is going to represent the ones place, and the leaves is going to represent the decimal place, the tenths place here. So this would be the same as 1.1. So we're going to have 1.1, 1.5, 2.3, 2.5, 2.7, 3.2, 3.3, 3.3, 3.5, 3.8, 4.0, 4.2, 4.5, 4.5, 4.7, 4.8, 5.5, 5.6, 6.5, 6.7, and 12.3. So our whole number portion is on the stem side, and our decimal portion is on the leaves side. And so we are asked, do the data seem to have any concentrations of values? And I would say that we could see that the majority of the data falls between 3 and 3.0 and 4.9. We can also notice from this data that we do have an outlier. The majority of our values fall below 7, but we have this outlier of 12.3. So we might also want to say that. So our stem and leaf plots are very helpful, like we said, for looking at all of the data on one little table. And so another type of stem and leaf plot that is interesting is a double stem and leaf plot. And so if we look at the data here in table 2.4, this is presidential ages at inauguration. So when they became president. And then table 2.5 is presidential ages at their death. And so we can come here and look at a side-by-side stem and leaf plot where we can compare those two sets of data. So you see on the left hand, we have our stem right here in the middle. And then we have two sets of leaves. We have the leaves for the ages at inauguration and the leaves for ages at death. And so this allows us to do some comparing to see their inauguration when they're coming into office and then when they are passing away, all in one table. Another helpful type of graph that we use in statistics quite a bit is called a line graph. Line graphs are used on an X and Y axis. That's called a Cartesian system. And so we have a horizontal axis that consists of the data values, and then we have a vertical axis that consists of the frequency points. So let's take a look at an example. So here, in a survey, 40 mothers were asked how many times per week a teenager must be reminded to do his or her chores. The results are shown in table 2.6 and in figure 2.2. So we see here that we have the number of teenagers reminded, and that goes from 0 to 5. So they had to be reminded 0 times, 1 time, 2 times, all the way up to 5 times. And the frequency, so how many teenagers needed to be reminded this many times. So we have 2 teenagers here, 5 had to be reminded once, 8 had to be reminded twice, 14 had to be reminded 3 times, and so on. So if we did a line graph here, we would see that the number of times the teenager is reminded is our horizontal axis, and then the frequency of being reminded, how many times they had to be reminded, is our vertical axis. And we see here that these are actual points that come from X and Y. So your X value is giving the number of teenagers, your Y value is giving the frequency. So we have some points here, 0, 2, 1, 5, 2, 8, 3, 14, 4, 7, and 5, 4. And so those are the points that are being plotted here. And then we connect those points with a line to get a shape of the graph. And we'd see that this is probably a pretty normal symmetric shape of a graph. It's steadily increasing, and then it peaks and it starts to decrease. So we're going to try several problems in Excel today. You will be allowed to use Excel for your exams and for your homework. And so we have chosen Excel because in most business corporations, Excel is a very acceptable program to use to do statistics. You will find in the business world, you rarely have to do statistics by hand because you're usually dealing with large data sets. So we are going to practice with Excel today during our lecture. So the first one we're going to try in Excel is we are going to construct a line graph. So I've already entered the data into an Excel file for today. And so I'm going to show you how we are going to use this. So I'm going to highlight my data. So I have the number of times it was in the shop and then the number of frequencies. So let's go back and look. We say here in a survey, 40 people were asked how many times per year they had their car in the shop for repair. The results are shown in table 2.7, construct a line graph. So we're going to construct a line graph here. And so we are constructing the line graph. We have our data in a little table in Excel. I pre-typed this. You would need to type this if you were working on your own. And we're going to click the data tab at the top of the Excel file. And then we're going to click the data analysis tool. Now, if you don't have the data analysis tool on your computer, you will need to download that. It is an add-on. And you can do that by clicking this arrow right here and going to more commands. And then you can go to add-ins. And it'll take you to a list, and you want to go to the analysis. You want to go to the analysis add-in. Let's click go to the add-ins. And we want the analysis tool pack. And then you would click OK. And then this data analysis, you would shut your Excel file and open it back up. And then this data analysis tool would be right here. So I'm going to click this data analysis tool. And I'm going to make a histogram. Nope, I don't want to make a histogram. I'm going to make some other things. So let me show you. We're going to right click here, right? Because we want to do a line graph. There we go. And we're going to go to quick analysis and choose charts. And we want a line graph. And then you can see if you want to add the points in there, you can add the points this way. You can add the points here. Let's see. I'd like to have the points and an axis. Okay, there we go. I like this one because you have your horizontal axis. You also have your vertical axis, and then you can see the points that are marked here clearly. All right. So this would be how we would make a line graph in Excel. And of course, you can edit this. If you wanted to title it, you could change your title here. You could add titles for your horizontal and vertical axes, which is good practice and things like that. And so you would just use this formatting tool to help you do those things. All right, let's get back to our lecture notes. So another way that we display data a lot of times is bar graphs. Now we're going to look at two types of graphs today. One is a bar graph and one is a histogram. And the important thing you need to realize between the difference between a bar graph and a histogram is most of the time we use a bar graph for qualitative data, so categorical data. And you should have already read about that in chapter 1. We use a histogram for quantitative data. And so when we use a histogram, it's important to realize that the horizontal axis represents the number line. So that is the main difference between bar graphs and histograms. We'll also notice that another difference between bar graphs and histograms is bar graphs often do not touch. The bars do not touch because it's categorical data. But in histograms, the bars do touch because they represent a number line. Okay. So let's look at some bar graphs to begin with. So by the end of 2011, Facebook had over 146 million users in the United States. Table 2.8 shows 3 age groups, the number of users in each age group, and the proportion of users in each age group. Construct a bar graph using this data. Okay. So this is also an example of a frequency table, right? We have our age groups here, which would be our class. Then we have the number of Facebook users, which would be our frequency. And then we have the proportion, which would be our relative frequency. So if we're taking a look at this,
and we created a graph using the proportions, the bar graph would look like this. And this is categorical data. We are giving them, they do have ages, but we're putting them in age groups. And so we have 13 to 25, 45% of our users are 13 to 25. 36% of our users are 26 to 44. And 19% of our users are 45 to 64. Let's take a look at another example. The columns in table 2.10 contain the race or ethnicity of students in U.S. public schools for the class of 2011. Percentages for the advanced placement exam, population for the classes, and percentages for the overall student populations create a bar graph with the student's race or ethnicity. Qualitative data. On the x-axis and the advanced placement examinee population percentage on the y-axis. So if we take a look at this example here, we see that even though we gave them numerical values, the data is qualitative data because we are using words to describe their race or ethnicity. We use numbers a lot of times to represent a word so that we can run things in Excel fairly easily. It makes our graphing a lot easier. And then we have overall student population here, and we have the AP exam population. So we can see here that the race and ethnicity is at the bottom, and it's labeled with the numbers that represent the races that we are discussing. And then we have the percent of AP examinees. And so we can see our percentages here. So one thing we want to notice here is here at this previous bar graph, it was really easy to see what the percentage was based off of the y-axis. Now on this one, the x-axis, because they are so, they're decimal points and they are so small, it would be difficult to see exactly what those values are. So the creator of this table put the values at the top of the table to help it be more recognizable. Okay, so we're going to do an example in Excel. And so our example says the population in Park City is made up of children, working age adults, and retirees. Table 2.9 shows the three age groups, the number of people in the town from each age group, and the proportion of people in each age group. Construct a bar graph showing the proportions. So I have already entered the data here. And I want you to notice that I entered the proportions as their decimal form, okay? And we know that proportions can be written as a fraction, a decimal, or a percentage. And I am using the proportions in their decimal form in this table. So I am going to show you how to create a bar graph. Again, you're just going to highlight your data that you want to use. And you're going to click here at this quick analysis tool. You can right click if that doesn't pop up easily and go down to quick analysis here. You're going to go to charts. And this time we're going to click more charts, all charts. And we want a bar graph. Okay. So if we want a bar graph, we're going to click OK. And we can see here that we have several options for our bar graph. You can make your bar graph go this direction, or you could click your bar graph using a, they call it a histogram here, but it is not a histogram because you'll see that the bars don't touch. We don't want that. Let's stick with this type. And it's okay that your bars are coming this direction instead of upward. I believe there are ways to change that, and we could change that if we wanted to, but for now, I'm going to leave it as is. So we could also choose one like this to show those decimal points more clearly because those are smaller values. All right. So let's head back to our PowerPoint. So earlier I was speaking about frequency tables, and frequency tables are a very good way to have a table representing your data. And a lot of the tables we've been looking at thus far have been frequency tables. So the frequency is the number of times the value or the data occurs. And the frequency table is the representation of this in table form. A lot of times we use frequency tables to create histograms. We also like to use what's called relative frequency, which is the ratio of the number of values that the number of times the data occurs over the total number of data values. And we're going to build some frequency tables later on. So we will walk through that step by step. So we want to create a histogram for the following data: the number of books bought by 50 part-time college students at ABC College. And so this is what we're going to look at first. So when we're creating a frequency table, we have to have a couple of things. We have to have our starting value and we have to have our ending value. And that's going to go right here in the number of books column. And we want to see that we have whole numbers of books, which makes a lot of sense, right? Because you're not going to have half a book that you purchase, right? And so we are going to look at this, and because on a histogram, our number line is our horizontal axis, we want to make sure our bars touch. And one of the ways we make our bars touch is by having these boundaries or these classes that go directly up to each other. So if we were looking here and we want to classify one, I am going to go, I'm going to choose a number that's a little less than one so that my bars will touch. So I have 0.5. And then I want to go to a number that is greater than one. And we see that this has an interval of 1. We have 1, 2, 3, 4, 5, 6. So I'm going to count by ones because we have an interval of 1. So I have 1.5 for my next lower bound, 2.5, 3.5, 4.5, 5.5. And so that value of 1 here is called your width. Okay. And so we want one value less than 1.5 for our upper bound for the number of books for our first class. And so we would call that 1.4. And then we're going to do the same thing. We're going to add our width to each of the upper bounds to get our list of upper bounds. And so now we have a clear interval that we can put these values in. So value 1 falls between 0.5 and 1.4, and that occurred 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Okay. 2 is the next value, and it occurred 10 times. The next class contains 3, and it occurred, so that's 10, 11, 12, 13, 14, 15, 16. 4 occurred 6 times. 5 occurred 5 times. And 6 occurred twice. So if we wanted to find the relative frequency here, we take the number of times that value occurred. So 1 occurred 11 times, and we put it over the total number. So we should have 50 because we're talking about 50 college students. So if we add up our frequency here, it should total to 50. And we do get 50 when we add 11, 10, 16, 6, 5, and 2. So we're going to put 11 over 50. Like I said earlier, relative frequency can be represented in 3 ways. It can be represented as a fraction, a decimal, or a percent. So the decimal form, which you would just find by taking 11 and dividing by 50, would be 0.22. And then the percent form, which you would find by moving your decimal place 2 places to the right, would be 22%. And so we can do that for the remainder of these values. So 10 over 50 is 0.2, which is 20%. 16 over 50 is 0.32, which is 32%. 6 over 50 is 0.12, which is 12%. 5 over 50 is 0.1, which is 10%. And 2 over 50 is 0.04, which is 4%. And if we did this correctly, we should be able to add this column and get 100, which we do. So this is our histogram that goes with our frequency table we just created. And you'll see you have your number of books at the bottom. The horizontal axis does represent a number line. And then we have the frequency, which it is occurring. And so that's what our bars represent. And you can see that our bars here are all the same width. It's important that they're the same width. That's why we worry about the width when we are creating our classes. It's important that they're the same width so that it is not a misleading graph. If they were different widths, it would appear that some bars would be larger than others, instead of just having a difference in vertical, which is what is being represented here, our frequency. It would have a difference horizontally, and that could be misleading visually. So we are going to make a histogram in Excel. This was also what you were asked to do for your first Excel homework problem. And so I noticed that the majority of you turned that in. And so I look forward to grading those. We are now going to, I'm going to show you how I do it. And that way, if you had some trouble or were not sure, you can go back and try that Excel problem again. So we're going to look at this example here. Let's go back and read our example. The following data are the shoe size for 50 male students. The size are continuous data since shoe size is measured. So that is a reminder from chapter 1, right? We talked about discrete and continuous data. So in chapter 1, discrete data is counts and continuous data is measurements. Construct a histogram and calculate the width of each bar or class interval. Suppose you choose 6 bars. So we are going to create this in Excel. So I've already done some pre-work in Excel. I typed all of our shoe sizes here, and we go up to 51. And so including the label, that's 50 values. So we didn't miss any. And we want 6 classes. We often call classes bins when we use Excel. So we want 6 classes. And so I chose 9, 10, 11, 12, 13, and 14 as our classes. And so these are going to be our midpoints for our classes. So if a number falls between 8.5 and 9.4, okay? So it falls between 8.5 and 9.4. That would be our lower limit and our upper limit. So then 9.5, 10.5, 11.5, 12.5, 14.5. Those are all of our lower limits. And then our upper limits. Again, we're going to add our width. So we have 9.5 or 9.4, 10.4, 10.5. I'm sorry, 11.4, right? 12.4, 13.4, and 14.4. So that's just to remind you of how our frequency table would look. So then if we wanted to put in the frequency here, we have 2 9s. And then from 9.5 to 10.4 will be the 9.5s and the 10s. So we have 1, 2, 3, 4, 5, 6, 7, 8 of those, and so on. Now, if I was creating this by hand, this is what my frequency table would look like. Since I'm going to use Excel to create it, I will show you that Excel will go ahead and generate a frequency table for you when you do the histogram if you use the data analysis tool. So we're going to go over to data and go to the data analysis tool, and we're going to do a histogram. And first we're going to input our range. So that's our data values. So I'm just going to highlight these data values so that they fill in automatically, the cells do. And then I am going to do the same thing for my bins. And so this lets me know that my bins are going to be labeled by my midpoints here. We want to make sure that I did not include the labels when I highlighted, so I'm going to take off label. If you included the labels, you would check label. And then we're going to have the output range. So the output range just tells where we want our frequency table and histogram to be output. So I'm going to just choose a cell that is open. And then we want the chart outputted as well as the histogram. So we're going to click OK. And we see here that we have our bins and we have our frequencies. And so this would be our histogram. Now, something I want you to notice is Excel does not immediately make the histogram bars touch. And we know that that's incorrect for a histogram. Histogram bars must touch. So what we can do is we can highlight those bars and double click on it, and this formatting tool will pop up, and you can take out the gap width down to 0%. And then our bars touch, which then represents a number line, and we are in good shape. Okay, let's head back to our notes and continue on with our lecture. So this is another example. We like line graphs very often, and you can also do a line graph can also be called a frequency polygon, and frequency polygons are used when we are talking about qualitative data, and line graphs can often be used for quantitative or qualitative data. So we see here that we have our lower bound and our upper bound. We have our frequency and our cumulative frequency here. So let's talk about what a cumulative frequency is, because this is the first time we've seen that word. Cumulative frequency just means that we are counting the frequency as we go. So in here, when we're talking about cumulative frequency, the frequency that we started with was 5. And then our next cumulative frequency is taking the frequency we already have and adding the next frequency. So 5 plus 10 to give us 15. So now we're going to take 15 plus 30 to give us 45. We're going to take 45 plus 40 to give us 85. And we're going to take 85 plus 15 to give us 100. So that is all it means for cumulative frequency. We are just cumulating, we are adding. And so here is the frequency polygon that goes with our example here. We often use frequency polygons so that we can compare data. So here we have two frequency polygons in different colors, but put on the same axis so that we can compare them. So a time series graph tracks something that occurs over a period of time. So in that case, your horizontal axis is representing time. So we can see here, these are intervals of 1 year. And then on the left-hand side, we see that we are analyzing a price index. And so we are looking at the price of a product over a period of time. And so we can see the price was increasing. And so those are very helpful, especially in business when you analyze price. Okay, so 2.2 is measures of the location of the data. And so we have several measures of location. We have percentiles, quartiles, median, and interquartile range. Interquartile range is actually a variation measure, but in your book, they include it under 2.2, so we will discuss it in 2.2. So percentiles, we can use percentiles. We often talk about them, especially, you've probably heard them mostly talked about in testing. So like you're in the top 99 percentile and so on and so forth. So we can use percentiles to help us find out, well, what is that top 99 percentile? Like, what is the score that you have to make to be in the top 99 percentile and so on. Quartiles is when we take our values and divide them into quarters. That's where the quart in quartiles come from. It comes from quarters. And so our quartile 1 or Q1 is 25th percentile. Our quartile 2, which is also called our median, is the 50th percentile. And our quartile 3 is the 75th percentile. And then we have what's called interquartile range. And so that is taking the middle 50% of the data. It's representing how much is in the middle 50% of the data. And so to find that, you take your Q3 and your Q1 and subtract. So when you're looking to find the IQR, you're taking your Q1 and Q3. And you are subtracting. So again, that Q1 is the 25th percentile. That Q2 is the 50th percentile. And this is often called the median. It's the middle value. And then Q3 is the 75th percentile. And so the interquartile range gives the middle 50% of your data. And to find your IQR, you're going to take your Q3 and your Q1 and subtract. So we often do what's called a 5-number summary in statistics. When we do a 5-number summary, we can represent that visually by making a box and whisker plot, but it contains 5 measurements. It contains our lower extreme, which is also called your minimum. It has your lower quartile, which is also called your Q1. It has your median, which we talked about, can also be labeled as Q2. It has your upper quartile, which is our Q3. And it has our upper extreme, which is our max. And so those are the 5 values we're talking about when I ask for a 5-number summary here. And you can see that the interquartile range is in the box portion of the box and whisker plot because it's from Q3 to Q1. So let's take a look at this example here. For the following 13 real estate prices, give the 5-number summary, calculate the IQR, and determine if any prices are potential outliers. Prices are in dollars. Okay, so the first thing we want to do is we want to order our data. If we're doing this by hand, we want to order our data. So I'm going to order our data. So our smallest value is 114,950. The next value is 158,000. Then we have 2,305,000. Nope, I'm sorry, I read that wrong. 230,500. 387,000. Then we have 389,500 or 950. 950. We have 479,000. We have 488,800. We have 529,000. We have 575,000. We have 639,000. 659,000. We have 1,095,000. And we have 5,500,000. So these are our values. So we want our 5-number summary to begin with. So we want our minimum. So our minimum value is the smallest value, which is 114,950. We want our Q1, our median, and our Q3. So these are our quartiles. Now I listed Q1, median, and Q3 because it's easiest to find the median first. So if I'm doing this by hand, I'm simply crossing off 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And so the value we're using is for our median is 488,800. So for our Q1, we're going to find the middle number for the bottom quartile. So we're looking here, 1, 1, 2, 2, 3, 3. So that value for our Q1 is 387,000. For our Q3, we're going to look at the upper values, the upper half of the data. So we have 1, 1, 2, 2, 3, 3. And so that value is 639,000. And our maximum is 5,500,000. If we want our interquartile range, we talked about how that was our Q3 minus our Q1. So our interquartile range is 639,000 minus 387,000. And so our IQR is 252,000. And I would say that we have an outlier, right? Our outlier in this case would be this 5 million. All of these values are steadily increasing, but 5 million takes a huge jump, right? So I would say that 5 million would be our outlier. Okay, I'm also going to do this example in Excel because if this was a much larger set of data, the crossing out method would take you very long and it can get quite frustrating. So let's look at this example in Excel. So this is example 214. So you can see I've already done a couple of things here to prepare. I've typed in all the values and ordered them already. I typed in the values randomly, and then to order them, I highlighted and clicked sort. And you can sort from largest to smallest or from smallest to largest. We want to do from smallest to largest. Okay. So then we are going to find the minimum value. That's the first value in our 5-number summary. So we're going to do equals, and then you start typing min. Then you can click on it. It opens parentheses. You highlight the data you want the minimum of. You close parentheses and click enter. And you see we get the same value that we got when we did it by hand. So for quartiles, you can do equals and start typing quartiles. So if we choose quartile, it wants an array first. So it wants the values that we want to look for the quartile in, and then it wants the quartile number. So you can see here, this is your 5-number summary right here, right? Minimum, first quartile, median, third quartile, and maximum value. And so if we're talking about the first quartile, we're going to use the number 1 and close our parentheses. And you see we got the same value we got when we did it by hand. You can use quartile still if you'd like, or you can use median. It does have the median command, so you can click median. And again, you're going to highlight the data you want to find the median of and click enter. So I'm going to continue doing these. We have our quartile 3, which again, you highlight your data. This time we want the third quartile, so we're going to input the number 3. We want our maximum, and again, you can use max as your command if you'd like, or you could use quartiles, and you're going to highlight, highlight and close. And then our IQR, we know that that's quartile 3 minus quartile 1, so we can just simply do that equation quite easily. Just do equal, and then highlight your value in quartile 3, and highlight your value from quartile 3 to start with. Put a minus sign, and then highlight your value from quartile 1, and then click enter. And you can see that we gave the same values, whether we do it by hand or do it in Excel. So let's pop back over to our PowerPoint lecture and continue on. So we now have talked about the 5-number summary, and we talked about quartiles. So let's talk about percentiles. So for percentiles, a lot of times we have large sets of data when we have percentiles, and a lot of times we end up getting our data in frequency tables. So you can use the kth percentile to help you find any percentile. So you want to make sure in your notes you have this formula for calculating percentiles, because this is how we are going to find our percentiles. It is a step-by-step thing. We're going to order our data. Step 1 is order our data from smallest to largest. Step 2, we're going to fill in this formula. Step 3 depends on what you get for the kth percentile. So if you get an integer, then the ith position is your kth percentile. If you do not get an integer, then you have to round I up, down, round it up, and then round it down to integers, to the nearest integers. And then you will have 2 values. So you will have 2 positions. So you will need to average those 2 positions. So let's take a look at an example. 50 statistics students were asked how much sleep they get per school night. Round to the nearest hour. The results were as follows. So we see here we have our frequency table. We want to find the 28th percentile, find the median, and the third quartile. So I'm going to do these by hand on this next slide. So if we want the 28th percentile, we are first going to order our data. Our data is already ordered. We can see that because it's in ascending order with a frequency here. Okay, so the next step is step 2, which is doing the calculation. So our K is 28. So I equals 28 over 100 times N is the number of data values we have. We have to see here, we have 50 statistics here. So when we add our frequency, we should get 50 as our total, okay? And so we're going to have N plus 1. And so when we do this, we get 14.28. So 14.28 is not an integer because it has a decimal attached to it. That is different than 0. And so that means that we're going to look at 3B in our steps. And so we're going to look at the 13th position and the 14th position. And we're going to average those values. So how do we know where the 13th position and the 14th position is? So we're looking for the number that's in the 13th and the 14th position. This is when cumulative frequency really comes in handy. So I'm going to do my cumulative frequency right here. So right next to it, I'm going to just add a little column for cumulative frequency. So again, that's just adding as we go. So we have 2 plus 5 is 7. 7 plus 7 is 14. 14 plus 12 is 26. 26 or plus 14 is 40. 7 plus 40 is 47. And 47 plus 3 is 50. So we see that we did get a total of 50. So we're in good shape. So we are looking for the data values that are in the 13th and the 14th. So if I look here, 13th position is going to be right here, right? 13 is between 7 and 14. The 15th position is going to be right here, right? Because it is between 14 and 26. So the two values that I'm going to average are 6 and 7. So we do 6 plus 7 over 2. And so we get 6.5 for our 28th percentile. Okay. If we want to do our median, we can do this logically when it's in a frequency table, right? If we have 50 values, we know our median is half of our values, right? So we're looking at the 50th. So that's 25th. So our 25th data value and our 26th data value falls right here at the 26. And so we have 7 as our median. And then if we want our Q3, we know that Q3 is the same as the 75th percentile, right? So if we did I equals 75 over 100 times 50 plus 1, okay, we would get close to 37.5. I did that in my head, so that might not be exactly right. It might be a little more or a little less, but then we would use the same rule. We would look at the 36th position and the 38th position. So 36th and 38 is both less than 40, but greater than 26. So that would put us at 8. So 8 would be our Q3. Okay. Like I said, this can be really difficult when it's a large list of numbers. So I'm going to also show you how to do this one in Excel. So I've already prepared it here. I went back and instead of having a frequency table, I entered all of the data values. So we had 2 4s and so on and so forth. And so I have my data values here. So to find the 28th percentile, we're going to do equals, and we're going to start writing percentile. And so you can choose percentile. It says array, so you're going to highlight the data values you're using. And then comma, and then it wants the K for the kth percentile. Remember that you can't write a percentile when you're writing as a number, you're writing it as a decimal. So I'm going to write 0.28. I'm going to write the decimal form of a percent. And we see that we get 6.72. The reason we get 6.72 instead of 6.5 is because Excel has a more exact way of finding that percentile. The way we do by hand is actually a rounded form. So there's a rounding error. So the 28th percentile is closer to 6.72 when you have that more complex formula. But we don't want to do complex formulas by hand. So we have our by hand formula. And then if we need a more exact answer, we can use Excel. So we're going to now do the median. We've done this already in the 5-number summary. So I'm just going to go ahead and do that. Again, you have to select all of the data values that you want to find the median of. And we see that our median is the same. It is 7. And we did quartile 3 before as well. So we're going to go ahead and do quartile 3. And again, you're going to highlight the values that you want input, comma, and then we're going to put 3 because we want the 3rd quartile. And we're going to close parentheses and enter. And you see we get the same value that we got when we did it by hand. Okay, let's hop back to our notes. So we have another example here. This example says we have 40 bus drivers were asked how many hours they spend each day running their routes. Round to the nearest hour and find the 65th percentile. So we're also going to do the 5-number summary in Excel. So again, I've already loaded our data. So you can see here we have all of our data for the 40 values. So for the 65th percentile, we're going to do equals, and again, percentile. We're going to highlight our values, comma. Again, we need to put it in decimal form, so we want 65th, so that's 0.65. Then we close our percentile, and we get 3.35. We can find our minimum the same way that we found it earlier when we did our 5-number summary by typing the command min. We can find our quartile 3, our quartile 1, I'm sorry. Highlighting all the values we want to find the quartile of, and then putting 1 and enter. We can find our median. Again, we're highlighting our data, and this time we just close parentheses. And then we can find our Q3 with the same quartile command. Comma, and we want the 3rd quartile. And then we can find our max with the max command. And you can see here that you have all 5 of your values here. And then you also have the 65th percentile. Okay. So let's pop back over to our notes. So that concludes 2.2. So let's look at 2.3. 2.3 is all about measures of center. So measures of center, we have 3 of them. The 3 measures of center are mean, median, and mode. We've already discussed median in-depthly. So let's also look at mean and mode in-depthly. So what happens is we talked about in chapter 1 that we have samples and populations. Your sample is a subset of your population. So we have a different mean for your sample and your population. So recall from chapter 1 that we discussed how your sample mean is represented as X bar. And this is your statistic, right? And then we have your population mean, which is a parameter. So remember, the big difference between a statistic and a parameter is the statistic comes from a sample. The parameter comes from the population. The statistic is known, right? It's known because it comes from data. And the parameter is estimated because we rarely know everything about our population. So we often have to make inferences. Remember talking about descriptive data and inferential data, the difference between them? So we are going to be calculating the sample mean because we are studying descriptive data right now. We will do estimations of population parameters in the future. So we will look at that later. And then your mode is the value that appears most frequently in the set of data. So here are the formulas that are for your population mean and your sample mean. And this is in sigma notation. And so I want you to see here that how you would read this formula would be your population mean mu is equal to 1 over capital N, which is n plus 1, lowercase n plus 1. And then we're going from I equals 1 to capital N of all xi's, and we are summing those. This is the summation sign, So this is the same thing as saying x1 plus x2 plus x3 all the way to xn all over n. The formula you're going to use the most is your X bar, your sample mean formula. So you want to make sure that you have your sample mean formula down. And so if you were doing this is the same thing as saying X bar equals, if we have 1 over n times the summation from 1 to n of xi's, that means we're taking our first data point, adding our second data point, adding our third data point, all the way up to our nth data point, and then dividing by n, the number of data points we have. So n here is called your sample size. Okay. So let's take a look at this example here. So this example says AIDS data indicates the number of months a patient with AIDS lives after taking a new antibody drug, and are as follows from smallest to largest. Calculate the mean and median. So if you wanted to do this by hand, you would add all these values together and then divide by the number of values you have. And you could do the cross-off method to find your median. I'm going to do these in Excel because, like I said, we very rarely do these things by hand. We often have business tools that help us, and the business tool we're using in this class is Excel. So I'm going to hop over to Excel and look at example 2.24. You can see I already input in my data here. So that's the months here. If I want to find the mean, the command in Excel is equals average. So a mean is just an average. So I'm going to double click on average here. I'm going to highlight my data values just like I've been doing. I'm going to close my parentheses and click enter. And so our mean is 23.575. If we want to find our median, we've done this several times already. So I'm going to go ahead and do it. And so we see that our median is 24. So let's pop back over to our notes and continue on. Here we have another example. It says, suppose that in a small town of 50 people, one person earns $5 million per year and the other 49 each earn $30,000. Which is the better measure of center, the mean or the median? And so this is important because when you have a measure of center, it lets us know a lot about the data. But when we have an outlier, that outlier changes the shape of the distribution and it pulls the data shape to one side or the other. And when it does that, it means that the mean gets pulled from one side to the other. So if I was to calculate this mean by hand, I would just do a weighted mean. I have one person who makes $5 million plus I have $30,000 and 49 people make that. So I'm just going to multiply by 49 instead of adding it 49 times. And then I'm going to divide by my sample size, which is 50. And so when I do that, I get a mean of 129,400. Okay. And so that's a very large mean when we're talking about the majority of people, everybody but one person makes $30,000. That mean is skewed. We call this skewed, and we're going to talk about that more in depthly in a minute. But why it's skewed is because that outlier pulls the data to one side. And so this mean is not a very good, reliable measure of center. But we know that our median here is going to be 30,000. And that's an excellent measure of center in this case, because the majority of the people in this town make $30,000. So we would say that the answer would be the median, because the mean is affected or affected. I don't know. I'm going with affected. Yeah, it's an effect. Yeah. The mean is affected by, it's affected. It doesn't matter, right? Write it correctly on your paper, right? I don't teach English, I teach math. By the outlier. All right. Okay. So if we want to find the mode, so the mode is just what occurs the most. So once your data is put in order, it's usually very easy to find the mode because it's whatever pops up where it's repeating several times. And so we see here that our mode is 72. It is occurring the most times. So our mode for this example is 72. Now there's a couple of things about mode that you should realize. You have what's called unimodal and bimodal. Okay. And so when you have unimodal, your graph usually looks like this. If you have bimodal, your graph often looks like this because it has two modes. And so if we took 72 out of this data set and we looked at the fact that 84 repeats 3 times, this is not a good example, but if I was to give another example, let's say we had 6, 6, 5, 3, 8, 7, 7, 9 for our data set. So then we ordered it 3, 5, 6, 6, 7, 7, 8, 9. We see here that we have two modes. Okay, so this is an example of bimodal because we have two numbers that occur more than the rest of the numbers. Okay. 5 real estate exam scores are given here: 430, 430, 480, 480, and 495. The data set is bimodal. Okay, so this is great. This is an example of bimodal, and that's because 430 and 480 each occur twice, and the other value in the set occurs once. Okay. Mode is the best measure of center when? When do we think mode is the best measure of center? Mode is the best measure of center when you are trying to convince people to do things a lot of times. So like if we were talking about weight loss, so if the mode was 6 pounds, okay, that would be a better measure of center than if we were trying to talk about the weight loss and on average people lost 2 pounds, right? So mode is often used in statistics to convince people to do things. So it is like the most likely to occur, right? And so we often want to convince people using things that occur most frequently. So here in 2.6, we're going to talk about skewness, mean, median, and mode, and how that affects it. So we have what's called a positive skew, a negative skew. This is also called right skewed. Oh, let me change. This is called right skewed because the tail is to the right. Symmetrical distribution is often called bell-shaped because it looks like a bell. And a negative skew is often called a left skew because the tail falls to the left, left skewed. Okay, and we can see that the measure of center, when it's symmetrical, all three of those values should be pretty close to the same: mean, median, and mode. When we have a positive skew or a right skew, our mean is pulled to the right because our outliers, we're going to have some kind of outlier out here, right? That is pulling this mean to the right. And then our mode is still where the peak is. The mode is always where the peak is. So with a negative skew, we have a negative or a small outlier. And so that outlier that pulls the rest of the data to the left. And so your mean gets pulled to the left. So this is an important slide. I may ask you on a future exam, how is the mean affected if you have a right skewed graph? And you would want to tell me that the mean is pulled to the right. Okay. So we use histograms a lot of times to help us know our distributions. We're going to talk about distributions more in depthly in the future, but for now, we are looking at this quick idea of symmetry and skewness. And so if I was looking here, this would be a symmetrical distribution. So I have what would be a bell shape that kind of goes around if I was to draw around this histogram. Here, this is skewed to the left because we have that shape that has the peak towards the right, and we have our outlier towards the left. This would be considered right skewed because our peak is towards the right and our outliers are towards the left. And so what is the shape of this graph? Again, you would be able to tell me that since the tail goes to the right, this is right skewed. Hopefully you would tell me that this is symmetrical or bell-shaped. And then this one is left skewed because the tail goes to the left. Okay. We would be able to say that this graph here is unimodal because there's only one peak. So unimodal is graph A. And bimodal is graph B because we see that we have two peaks. All right, the last thing we're going to talk about today is the measure of spread of data. And so there's two main things that we talk about when we talk about measure of spread, and that's standard deviation and variance. And so just like we had a sample statistic and a population parameter for median, we have a sample statistic and population parameter for standard deviation and variance as well. So when we're talking about standard deviation, we use a lowercase s to represent the sample standard deviation. And we use a sigma to represent the population standard deviation. And so these are the very complex formulas for standard deviation. And you can see here that if I was to read this to you, it would be that the sample standard deviation equals the square root of the sum of x from 1 to n of x squared minus n times the mean squared divided by n minus 1. That's very complicated, and it's very difficult to do by hand. A lot of times when we do it by hand, we are going to use a table. So let's talk about variance real quickly. So variance is also a measure of spread, and it is simply the standard deviation squared. Oh, yeah, standard deviation squared. So sample variance is s squared. Sample standard deviation is s. Population variance is sigma squared, and population standard deviation is represented by sigma. So here is an example of how you would calculate this by hand. First, you would find your mean. And so you would take all your values and add them together and divide by how many values you have. Then you would find your standard deviation by taking your deviation, which is your x minus your x bar. So you take every data point and subtract your mean from every single data point. So we have 9, 9.5, 10, and so on. So we do that. And then we have our deviation, which is that value squared. So we're going to square that value here. So we have the value from this column. So you find this value and you're going to square it. So we're squaring the values from this column to get a new value. And then we are taking those values and multiplying by the frequency of those values. And so you can see here that we're multiplying by the frequency. Okay. And so then we sum all of those because we have the summation. And so we get a total here. So our standard deviation is 9.7375. Nope, that's our variance because that is squared. If we want our standard deviation, we then take the square root. So this is our variance. And this is our standard deviation because don't forget, you have to divide by n-1 right here. Okay. And then you have to take the square root for your standard deviation. All right. So let's do an example together, but this example I'm going to do in Excel because again, finding standard deviation by hand is tedious and you will never do that in the business world. In the business world, you will always use a tool to help you, and the tool we're using in this class is Excel. So it says here, use the following data, the first exam scores from Susan Bean's spring pre-cal class, to create a chart containing the data, frequency, relative frequency, and cumulative relative frequency to 3 decimal places, and calculate the following to 1 decimal place: the mean, standard deviation, median, first quartile, third quartile, and interquartile range. So I'm going to hop over here and go to 2.30. So you can see here, I've already done some pre-work before class. I have my list of data right here. And so we were asked to do a table for data, frequency, relative frequency, cumulative frequency. And then I threw in cumulative frequency because we talked about that, but it didn't ask for it. But I wanted to throw it in there. So then we have cumulative relative frequency as well. So let's take a look at this. So I've already done the data and the frequency of the data. And so we know that that's simply just taking the data points and seeing how many times they occur. So for relative frequency, remember that relative frequency is the number over your total number of the frequency over your total number. So I'm going to put total right here because this will make my life a little bit easier. And we should have 30. We see that we have 30 total right here, 30. We should have 30 data points right here. If you weren't sure, you could do equals sum, and you could make sure that you didn't miss any data values. And you see that we get 30 here. So for the relative frequency, for each one of these, you're doing equals 1 divided by the total. And then equals your frequency divided by the total. Okay. And so if we highlight this and copy, then we can highlight here, right click, and copy the formula. Let's see, we don't want that. It is trying, we want to divide by the 25th percentile every time. So let me just change this to 30. Oh. All right, I'm going to change this formula here. Here I'm going to ignore the error. Okay. Here I'm going to do equals, and I'm going to use my frequency, but since I know what the total is, it's 30, I'm going to divide by 30 so that I can copy and paste. Okay, and so we have this value here. And so I'm going to copy that. And now I'm going to paste the formula. And you can see here, now we get the same value, we get the correct frequencies. And if you want to go to 3 decimal places, like you were asked to go on the question, then you can shorten your decimal places and increase your decimal places by using these 2 errors here. So we want 3 decimal places. So we have 3 decimal places. So then cumulative frequency is going to be taking our frequency and adding them, right? So we have 1 here. So we have 1 here, 1. And then here we're doing this one time plus this one, right? So we're going to do 1. So equals cumulative frequency plus this value, or cumulative frequency here, your first one, plus this value here. And so then here we have this value plus this value. Okay. And so now we should be able to copy this and highlight and do the formula. And so we get the cumulative frequency here. Cumulative relative frequency. So this one's going to equal this value. Enter. This one's going to equal this value plus this value. Enter. And so now we're going to copy this and paste it here, the formula, and then it continues to add, and we see that our total gets to 1 for our cumulative frequency. So again, if we want 3 decimal places, all we need to do is go back and take this to 3 decimal places. Okay. So the next thing we were asked to do was find the sample mean, sample standard deviation, median, and the quartiles and interquartile range. So again, we can use average for our sample mean. And I'm just going to highlight this and click enter. And then for our sample standard deviation, we click equals standard deviation. Let's see, SD. Let me think, standard. No, yes, there we go. STDEV dot S, because we want a sample standard deviation. And again, we're going to highlight the same thing and click enter. Okay, we want the median. So we use the median command. Okay, we want our Q1, so we're going to use the quartile command. And we want our Q3. So again, the quartile command. And this time 3. And then interquartile range is your Q3. So we have equals Q3 minus Q1. And so our interquartile range is 26.5. And we want 2 decimal places for these values. So we're going to decrease. Hold on, let me try again. Just highlight these values. So we're going to decrease to 2 decimal places. And so now we have completed that example in Excel. All right. So let's continue on. Here, we could do it by hand. I decided to do it by Excel. So let's just put a snip and put the answer on that slide. Come on. There we go. And so that is the answer to the previous example. All right, so let's continue on. 2.7 is about being able to compare values for different data sets. And so we use what's called a z-score or a standardized value to help us find that. Your z-score is simply your data value you're interested in standardizing minus the mean of that set of data divided by the standard deviation of that set of data. And so again, you do have a sample z-score and a population z-score that you can calculate. We're going to do sample z-score a lot of times because we have data. Occasionally we do population z-score when we are given some information. So we will talk about when to use which in the future. But for now, we're just going to use the sample z-score. This helps us. The reason we want to standardize this is because we know that we have symmetric data, and that symmetric data is called normally distributed, but there are several different normal distributions. You could be over here and have a normal distribution, or you could be over here and have a normal distribution, or you could have a really large normal distribution like this. And if we wanted to be able to compare those different normal distributions all into one, we can standardize it. And how we standardize it is by getting this purple graph. And so we take our mean and our standard deviation, we get our z-scores. So these are all sorts of different means and standard deviations here. And then you can change it to a z-score, which then gives it a value from -3 to 3. And that will be able to standardize the scores for us. Okay, so we're going to use this to help us decide who did better in their GPA. So 2 students, John and Allie, from different high schools wanted to find out who had the highest GPA when compared to his high school. Which student had the highest GPA when compared to his high school? So we are going to use z-scores. So first I'm going to do John's z-score. So you take your data value you're interested in, so that's 2.85, minus the mean for that school, which is 3, over the standard deviation for that school, which is 0.7. And so if you were going to put this directly into a calculator or do it in Excel or whatever, make sure you're using parentheses so that order of operations is done correctly. Because I see students make that mistake quite frequently, actually. So I just want to forewarn you that that is often a mistake I see. So when you do this, you should get -0.214. And then Allie, you take 77, you subtract 80 over 10, and you get -0.3. The greater of the two values is the one who has the highest GPA in compared to their school. So in that case, it would be John, because negative numbers, the smaller the value, the greater it is. If you're not sure, you can always look at a normal distribution to help you, right? So -3 would fall right here for John. And Allie would fall at, -3 would fall for Allie. Ooh. And then John falls at -2.14. So that would be like right here where John falls. And so you can see that John has a higher score. Okay. And so John is your correct answer here. So when we're talking about measures of spread, there's a few things we want to talk about. The reason we need measures of spread is to help us understand variability. And there's lots of reasons why we could have variability in data. We have what's called observational or measurement variability. So that would be an example of that would be like if we were using a scale and maybe we used 2 scales. So we had 2 sets of data. We're going to put all the data together, but so that we know the weight faster, we're going to use 2 scales. And so there could be a measuring variability between the 2 scales, right? They might not be set exactly. So that's an example of measurement variability. There's what's called natural variability. And so that's a natural difference in things, right? So we have lots of different kinds of variables, and we want to try to control them the best we can in experiments. But there are natural variabilities, right? So when we are talking about like women versus men, as far as we're talking about their body makeup, a lot of times men tend to be taller than women. And so that would be a natural variability. So there are natural variabilities in our data a lot of times. And then there's induced variability. So that is like your treatment or your placebo, right? We want to induce a variable a lot of times. So that's the variable of interest. And so that would be like your treatment. And then sample variability happens when you have multiple samples, right? So if I took several different samples, it's very unlikely that I get the exact same data from several different samples, right? So we would want to account for that as well. So for any data set, no matter what the distribution of the data is, your standard deviation and your mean, if they're two apart, 75% of your data should fall in there. With 3 standard deviations from the mean, 89% of your data should fall in there. And 4.5 standard deviations of your mean, 95% of your data should fall in there. And this is called the Chebyshev rule. We're not really going to talk about that in depthly, but what we are going to talk about in depthly is the empirical rule. And the empirical rule talks about how approximately 68% of data is within 1 standard deviation of the mean when it's normally distributed. 95% of the data is within 2 standard deviations of the mean, and 99% of the data is within 3 standard deviations of the mean. So this is a pictorial representation of the empirical rule. And so we use the empirical rule a lot of the time because a fun fact in statistics, which we will dive into more in depthly in the future, is that the more data values you have, the more likely it is that your data is going to be normal. That's a natural phenomenon that occurs with big sets of data. And so with that being the case, we can standardize a lot of data and force it to be normal by taking a very large sample. And so this empirical rule comes in handy because if we just know the standard deviation and the mean, we can predict how much of our data should fall between certain values. And so this is a great pictorial representation, and we're actually going to use it to help us do the next example. So 2.7 empirical rule example. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 60 and 145? There is a mistake on these. I meant to type 70 here. So if you'll just go ahead and fix that on your own notes so that we can do this together. Okay, so for this problem here, we're going to find these 2 z-scores. So our first z-score is going to take 70 minus our mean over our standard deviation. And we get a standard deviation of negative, or a standard score of -2. And then, oh, my screen jumped. And then for Z2, we're using our second value, 145 minus 100 over 15. So we get +3. So what has occurred here is we took a normal distribution where the mean was at 100, and we're looking at values at 70 and 145. And we want to know how many values, or the percentage of values, that fall between these two here. So by going to the z-score, what we've done is standardize this so that now we have 0, -2, and 3, which allows us to use the empirical rule. So the empirical rule we are going to use, if you were within 2 negative standard deviations, okay, so this area here, if you were within 2 negative standard deviations on both sides, because it's symmetric, 68% of your data would fall, 95, hold on, let me think. 68, 95 within 2 standard deviations. We see here 95 within 2 standard deviations. And so if we split that in half, 95 divided by 2, then this that's highlighted in green is 47.5%. If we're looking at 3 standard deviations, so we're looking here in blue, okay, our empirical rule tells us that within 3 standard deviations is 99.7% of our data. So we want half of that. So 99.7 divided by 2. And we get 49.85%. And so we can now add those together to find out what that total is between these 2 test scores. And we get 97.35% of our data. All right, so that concludes chapter 2. I hope you've enjoyed this lecture. If you have any questions, please don't hesitate to reach out, and I will look forward to recording another lecture for you for chapter 3.